Thanks, Dan.
And we'll just change the lights.
And I think I need to wear this so it can be recorded. Is that right?
That's perfect.
Can you all hear me okay? And nice to see some old friends here. Talking about, I'm going to cover quite a range of issues. Yes, about innovation and how it relates, innovations that have succeeded and innovations that have failed. And certainly, I do feel a duty of care to talk about these items because I want to concentrate on 4 points. Why innovation requires extra care, that pre-stressing is a wonderful tool, but it has special dangers. And innovation demands that there is no confusion on risk, with the responsibilities of the contracting parties being clear, with no risk being shared. And I want to talk about peer reviews and why I believe they represent real risks that you should be aware of. I'll go through these examples quite quickly, and if you have any, you'd like me to expand on any of them at the end, there'll be plenty of time for questions. My direct experience has led me to believe that those matters are of fundamental importance to all who want to work in the heavy civil engineering arena. Most engineering is copying designs that have been proven in practice elsewhere. They may have evolved over time from the innovative work of others, yes, adapting and maybe improving a previous innovation, but this is a much easier route than doing something new. If you do wish to try something new, you'll need to take much more care. And we should always recognize that the designer's role is much different to the contractor's. My background is as a designer, and I've always felt the contractor has the tougher job. Successful construction will often depend on how clearly each party involved, and there may be more than two, understands their roles, or in other words, total clarity on who is taking what risk. Normally, designers analyze the completed structure. They will have an idea of how it might be constructed, but they will not dictate how it is to be constructed. If they do, they will take over some responsibility for the contractor's method of work, which is unsound. The method of construction must be selected by the contractor, and he is responsible for it. However, sometimes in civil engineering projects, the method of construction may cause or lock in stresses that cause problems for the designer. Such cases require more than normal care. And finally, when you're collaborating with separate companies, you must never assume you are working with reliable, sound, professional people. Hopefully they will be. But if you do not prepare yourself for the worst, you will suffer. A particular risk, if you start a peer review with a poor commission, you may end up carrying some responsibility for the design without the authority or information to control the responsibility you may have inadvertently assumed. Okay, it's all heavy stuff. Some examples. Here's my starting point, the South Rangitikei or the Mangaweka Bridge. I'd just like to go through the history of how this new railway deviation evolved. It called for 3 bridges. This one, which is 315 metres long, with a 56-metre maximum span, and the piers are 80 metres high. And then 2 other bridges like this, which are, again, across deep ravines. Now, this was a New Zealand Railways project, and it was a daunting one for them. Not only were there these three major bridges, there were problems with access, slope stability, lateral and vertical erosion, and others. Another government agency thought another alignment should be selected, not the one the railways wanted. So this was quite a sensitive issue that aroused significant debate between the two government agencies involved. For New Zealand Railways to win this argument, they had to get a good bid for the largest bridge, which is the Rangitikei Bridge. And if they didn't get a price within their budget, then the pressure would have come on for a different alignment of the railway deviation to be considered. So they prepared their own design for the Mangaweka Bridge, which was a steel girder bridge with inclined hollow circular piers. Really an unusual design and hard to build. And they recognized this, so they actively sought an alternative design and encouraging all those tendering to submit their own designs. So I, as part of Beca, prepared an alternative design working with Cadelpha Construction in June 1972. Our tendered price was a minuscule 1.435 million. Seems tiny these days. It was not insignificant in those days. It was by far the lowest. And New Zealand Railways were just delighted because it meant their alignment would be, they'd won their argument. And then prior to acceptance, NZR requested Cadelpha and Beca to consider incorporating a base-isolated design that they favoured. This was a concept that had been extensively studied by them, working with the DSIR, and in particular with Ivan Skinner, who had developed and tested steel torsion bars to be used as energy dissipators to isolate the piers. And they also asked that Beca be released from their role from their contract with Cadelpha and be employed by NZR on a normal consultancy role. After some study, we found these two requests could be accommodated really easily with little cost penalty. We are quite happy to work for NZR, of course, and Cadelpha demanded a reasonable sum for that to take place. But we ended up with a new contract price of $1.516 million, incorporating the base-isolated concept. The design was based on unusually high earthquake resistance standards, with the earthquake design including full design live load at the time of the design earthquake. There were many innovative aspects to Cadelpha's method of construction, and they started to use as false work a launching girder which they had previously used here in Auckland on the Pakuranga or Tamaki Bridge in Auckland. Now, I'll just show that bridge. Here it is here. It's a precast concrete segment bridge placed by launching girder from above. And if you, there's the launching girder that you can see. Now, this launching girder, and here was where Cadelpha, who were an Italian company, Cadelpha stood for Costruzione del Favro. It was the Del Favro family that owned them. So they had very good links to Europe. And this concept, which was developed by the French, was an innovation by Jean Muller of Compagnon Bernard. He it was adopted for a famous viaduct in Switzerland called the Crillon Viaduct, which is a very long viaduct where, I can't remember the number of spans, but something like 50 of about, similar span to this, 50 of about 70 metres. And so the cost of the launching girder could be written off over many spans, and that bridge was quite extraordinarily cheap. So what Godolphin did was they bought the plans of that launching girder used at Crillon, constructed a new bridge in Italy, bought the parts out here and assembled them. And it worked very well on this job. They could place 8-9 units a day when they're in full flight. Now then we come to Mangaweka. Now, I'd been actively involved in this bridge with Godolphin, so I knew them well, and that was why we worked together on the alternative bid for Mangaweka. Now, when it comes to the South Rangitikei Bridge, their idea was to turn the launching girder round the other way. Now, this is not, in fact, the launching girder that they used. This is the design that was done later. Now, it was a very complex structure. It incorporates stays, you can see, that needed repeated stressing depending on the loading case. It was also very flexible, which complicated the working procedures to control deflection as concrete was poured. It was effectively a rolling structure and had to be designed for nearly 30 different load cases. So you can see that the design of this launching girder was a substantial task in itself, and perhaps even as demanding, if not more so, than the design of the permanent works. I hope it'll be clear to you that the South Rangitikei Viaduct is an original. It did not have the luxury of being a copy of a bridge completed by others. Indeed, there were many innovative aspects about the permanent works and their construction. The 76-metre high piers were slip-formed, and extensive studies were done of how they might respond in earthquake conditions in their temporary construction phase, namely when they were still pure vertical cantilevers, yet to be made continuous with the bridge deck. The issue here was that the lateral movements of the slender piers caused by wind or earthquake might be sufficient to trigger a buckling collapse. It was found, however, that their flexibility and strength was such that in this temporary cantilever state, their stability was adequate. This was, of course, the contractor's responsibility. And the contractor gave consideration to guying these piers during construction, but Godolphin did not favour that because of the fear of incremental collapse if they dropped something on a stay, on a guy. And this was prescient. The piers were pre-stressed onto their piles to permit erection as a vertical cantilever. In their final condition, they sat on a large rubber bearing. The transition from one to the other was done after the bridge above had been completed by sand jacks in the pier base. Quite some testing was needed to ensure that the sand did in fact run out of the jack, but in the end this detail worked well, and the rubber bearings can be replaced, of course, by a similar operation in reverse if needed. And the base isolation gave three great advantages. It could be designed to have a high level of seismic resistance, in essence for moderate shaking, up to a structural acceleration of 8% of gravity, the structure remains in contact with its bearings. When the shaking becomes more intense, the piers can lift off or step, and the transverse natural period of vibration prior to stepping is 1.6 seconds. when any pier steps up or steps down, the energy dissipators, and the two in each leg, come into play. Each has a capacity of 450 kilonewtons, and the force is maintained by plastic yielding of the steel torsion bars in the dissipators. And this gives good damping via what are replaceable items and means the piers remain undamaged in major earthquake events. That's the theory. The second great advantage is the concept limits the maximum feasible buckling load that can be imposed on the piers. It is simply all the dead load plus the live load plus the 900 kilonewton force in the dissipators. So that limitation of the maximum load meant the piers could be unusually slender and lightly reinforced. And then, because the piers were... You okay? And then, because the piers were expected to remain essentially elastic in earthquake conditions, the pier-to-beam joints was greatly simplified. And these joints are not easy to construct at height, and you can see them gearing up for one of those there, because you're slip-forming the piers, and if you've got to build a strong beam column joint at height, that is not easy. And this was nearly 50 years ago, and we knew there were problems with beam column joints, but we weren't quite sure how to design them. That came somewhat later. But by keeping the pier elastic, then that beam column joint situation was solved. I was a youthful 30-year-old when the design was proceeding, and quite understandably, the New Zealand Railways engineer, bridge engineer, asked John Hollings, my senior partner, to peer review my design. John declined to do this, but instead engaged Nigel Priestley, who did so using his PhD students to do the number crunching, and did a very thorough and sound job, and we had much discussion about the project. It was the start of many projects I worked on with Nigel, which was always a pleasure, although demanding. And then on the 5th of May 1975, Cadelphil were concreting a segment on the launching girder when a pair of diagonals buckled and the deck collapsed. These diagonals had been designed by Cadelphil to take much higher loads in a different load case, but in tension, not compression. And I remember well the resident engineer calling me at 10 a.m. on the morning of 5th of May 1975, that date is embedded in my mind, saying there'd been a slump of the girder during concreting. I asked him, is everyone off the structure? Then I asked him to keep well away, but watch what was happening. My fear was that if the first pier collapsed, it could incrementally knock down the other piers. He called me back 20 minutes later and said, it's gone. I said, how much is gone? He was surprised at this question, but fortunately all the repairs remained, and it was only the bridge the deck that needed repair. It was indeed fortunate that no one was injured, and that the pier had not been guyed, as quite a bit of material fell from the deck and could have landed on them, and if those guys had snapped, that could have then caused the incremental collapse that Cadelphil was so worried about. As is often the case, once it happened, the cause of the failure was very obvious. And New Zealand Railways asked why we had not checked it, and implied that we, and it was more an implication, or rather me, that I was personally at fault. And this was an emotionally held view that logic could not abate. In fact, the following matters need to be appreciated. The contractor was responsible for the false work design, not the consultant. The consultant could not have checked the false work, even if he had wanted to do so, as he did not have the details of the structural members nor their material properties. Remember, these were parts that had been constructed in Italy 10 years earlier. Effectively, this was a rolling false work system with many different load cases, and its design constituted a major task in which the consultant had not been and should not have been involved. We went into an extensive limbo period until February 1980 because of differences between the contracting parties as to the appropriate standards that should be adopted on site henceforth and who should pay for them. An attempt was made to salvage the launching girder, but this was abandoned as it became clear that the material of which it was made and its stress-raising connections were unsuitable. In fact, the steel was very difficult to weld. It was a highly brittle steel. Now, this was a very trying time, as you might imagine, and I always remember we engaged a consultant, Dr. William Fairhurst, who was a retired Scottish engineer who'd built some very big bridges in Scotland, and he had retired to Auckland, and I consulted him, and I'll never forget him saying to me, he was a very formal gentleman, "Mr. Cormack, you are being accused totally unjustly of lack of care. I appreciate how trying this is for you and the stress you are under. But remember this, although it will be of little comfort to you now, you will look back on this event as the most formative of your career." And so it was. On the 6th of May 1975, the following day, a motorway bridge near Karangahape Road in Auckland collapsed on its false work, just after a pre-stressing operation. I was asked to investigate, but that day I was down south at Mangaweka. And what had happened is shown in this sketch. It was a classic case. I was asked to be involved, but I was occupied elsewhere. However, later on, I got involved with the Ministry of Works, who were the designers of the permanent works of this bridge, at a subsequent arbitration. The arbitration seeking to decide who should pay for this massive collapse, where the total bridge had to be demolished and rebuilt. It was a classic example of the effects of pre-stressing, and I think you all know how it works. Two people come onto site in overalls, perhaps three, and they have a small jack that they wheel along and a little pump, and they stress largely invisible cables, but they impart enormous forces to the structure. In this case, the pre-stressing cables were being stressed at the three-quarter point, as shown on this sketch. So there's a massive transfer, and those cables, a coupler was placed at this point. All the cables were stressed at this point, so there's a total transfer of stress onto the scaffolding. And it's exacerbated by the fact that the soil conditions were not uniform across the site. In fact, there was a sandstone seam on one side which dropped away onto clay. And because the bridge is a box girder, it is torsionally very stiff, so the load went to the props on stronger sandstone. Failure was total. Fortunately, it happened relatively slowly and no one was hurt, but the ramp had to be totally demolished and rebuilt. If you like, the construction sequence was an example of innovation that failed. The main point with the arbitration was who was responsible for recognizing in advance the high forces that would be imparted to the false work by the specified sequence of stressing, the designer or the contractor. Who has this responsibility? Well, it depends on the contract. In this case, the contract had nothing specific to say on this issue. So a very interesting case, and if you'd like to hear more about how that conflict was resolved, and I'd be happy to cover that later in question time. And then there's the humble grouting machine that comes on later after the pre-stressing, again by these people with these little pumps. And this can cause unexpected effects. So this is a precast water reservoir in New Plymouth at Veal Road. It was similar to many that have been built using thin precast panels stressed together to form a cylinder. This concept has been used for more than 50 years. The circular compressive stresses are high, especially at the base of the tank, but the concept has worked well. So please take a minute to look at this sketch. You can see this is a plan view of a joint. So you have the precast, pre-tensioned concrete slabs connected by a duct with horizontal pre-stressing, circumferential pre-stressing, and in this case, the contractor or the designer decided he wanted an innovation. He wanted to have a dry pack joint, whereas the normal solution would be to have a cast in situ joint. Quite difficult to form those joints. And so the innovation was dry pack. It had to be placed by workmen working up high ladders. These units are about, I'm not sure, 9 meters high, something of that sort, perhaps 10 meters. I can't remember the exact figure, but they're quite tall. And so you had a workman up ladders, one on the inside, one on the outside, putting in the dry pack, work that's hard to do and hard to supervise. Then there's the problem of connecting the ducts at that joint. So that they've got to be watertight. So there's a messy little detail there so that they're watertight or at least grout tight. The cause of this dramatic failure was not immediately apparent. I arrived on site and it looked wonderful from the outside. I then got up a ladder and went over into the inside, and there was a total collapse of the inside of the wall. And the cause for this was not immediately apparent. After a lot of thinking, my hypothesis was that the dry pack on the inside face was less well packed than on the outer face. And on stressing, internal cracks developed, internal vertical cracks developed that connected those grouting ducts. And when those cables were grouted, that formed a giant flat jack into the cracks that totally delaminated the inside of the reservoir. It was a failure of staggering dimensions. And this was the first to be grouted, so they grouted in a sequence, so it was only about a third of the reservoir that had failed. The council engineer was very enterprising, and he got a piano tuner who came and tested for drummy concrete to find if there are other cracks throughout the wall. And in fact, he found cracks all the way around the reservoir. And so in the end, the reservoir was demolished and rebuilt with cast in situ joints. I now want to move to the Sky Tower and expand on the issue of risk definition. You can see here the top of the mast and alongside the crane that erected it, Our studies showed that the wind-induced stress reversals of this slender structure presented a severe fatigue case. To dimension this for you, the deflection calculated at the top of the mast under the design wind speed of 60 metres per second was over 3 metres. Accordingly, we introduced tuned mast dampers, essentially viscous fluid sloshing through baffled annular rings within the mast to reduce the amplitude of displacement and therefore the quantum of stress reversal. And of course, we paid careful attention to steel selection, welding techniques, and the avoidance of stress-raising details. A lot of thought was given to how the mast would be erected. As I said before, for many structures civil engineers encounter, it suffices to design the structure assuming instantaneous construction. That is to say, they are designed for service loads, and separate checks need to be made to confirm the structure is not damaged by the method of erection. For many bridges, the loads imparted by the method of construction will be more severe than those of the design live load. For cantilever-constructed bridges, this is frequently the case. For the Sky Tower mast, however, there was the problem that the method of erection, which was the contractor's responsibility, would cause levels of stress that would unacceptably reduce the number of stress reversals it would be able to resist in the future. You can see the mast had to support the crane for quite some period of time. And that was the issue. So we had a collaborative approach, enabled us to agree with Fletcher, a very skilled contractor, the maximum load they could impose on the mast, and for them to define how they would not exceed it. You might have worked on that, Aaron. This all took quite some time, with an outstanding result. I now want to move to the difficulties inherent in peer reviews. If you are considering accepting such a commission, I strongly suggest you assume your peer review will uncover defects and plan what you will do before you start your studies. Otherwise, you risk taking over inadvertently the responsibilities of the original designer or even the contractor. I'll give 2 examples of this. Our geotechnical specialists accepted what looked like a straightforward commission to comment on the failure of a propping system developed by a contractor for a 25-metre tall retaining walls in Singapore. Now, this shows a 25-metre trench where a motorway was being built and a propped retaining wall which failed. The reason for the failure was obvious. It was simply an unstiffened webs that failed in buckling. A really common problem with propping design. However, when we got into the problem, so a commission was accepted, yeah, we can report on that. And then it became apparent the amount of soil movement laterally and vertically was substantial. And right adjacent to the cutting were high-rise buildings, and which were very insecurely founded. They were tall buildings founded on driven piles, which were groups of railway irons. They had very low lateral resistance and could have been damaged by the lateral soil movement. And they were potentially at risk of catastrophic failure. The buildings were old, and when we inspected them, they showed signs of damage. But it couldn't be ascertained whether that was original or recent. And no condition survey had been done of them. So we had a client who didn't want to take any responsibility for anything, and a contractor saying, "What shall I do? Help me." Had there been a collapse, there would have been extensive loss of life, and guess who would have been the first to have been interrogated? Why did you not evacuate the buildings? Inadvertently, by expecting a simple peer review job, we were deeply involved in a major problem, and fixing it was very demanding. How should we have commissioned it? Again, I'd be happy to give you my ideas on that in question time. And then another one is Andrew Dixon's favourite project, Eden Park boxes. A labour of love for me, as Eden Park was in desperate need of funds and received no support from central or local government. So we developed this concept in 1987. It had to be constructed. This is a viewing box structure that we could sell in advance. It was a very good commercial deal. It had to be constructed cantilevering from the rear over the top of the old stand with no access from the field side so that sports events would not be interrupted. It is effectively a pre-stressed concrete stayed girder cantilevering 20 metres. The Trust Board approved its construction as it showed a positive rate of return from year one, and it was in 1987, October 1987, just after the financial collapse, and interest rates were 21% per annum. And this showed a very positive return in that condition. The key design element was the deflection of the cantilever supporting the boxes, as their natural period of vibration coincided with the beat that would be produced by some concerts. And the likelihood of several hundred patrons jumping up and down was quite high. However, our analysis showed, didn't it, Andrew, that very large deflections, even of a metre, could be sustained without damage. So we thought that if those patrons did get resonance going, those deflections would be so large they would be encouraged to desist. They're jumping up and down. No deflection problems arose in service, but this was because, for various unrelated reasons, concerts at the time, and still, were unconsentable. So we never had that problem. But another problem did cause me major concern. Over the years, a series of additions were made to the boxes by the parties. These were to add a lower level for cameras, and then later another story on top for press boxes and additional viewing capacity. So instead of the single floor initially allowed for in the design, in places we had 3 floors. Progressively, the margin of safety was being lowered. And even though each of these additions were designed by professionals and peer-reviewed, I could not be sure that any of them had done a holistic study of the total structure. Were they aware of the ground conditions and the adequacy of the tie-downs that had been constructed and on which stability relied? This is a single degree of freedom structure, little redundancy, normally to be avoided. And on those occasions when the boxes were full, so would the stand below be full. So the consequences of failure could not have been more severe. Because I'd been pushing for detailed review and careful peer reviews, I was in no doubt that had there been a failure, I would have been the investigator's first port of call. And I had insufficient confidence in the peer reviews that had been done. I was able to instruct that controls of loading, numbers of people, were put in place, but even so, if there'd been a strong southerly wind in midwinter and during a test match, I was concerned the factor of safety was not large enough for comfort. The final word was the Rugby World Cup in 2011. A new stadium meant the boxes had to be demolished. So to my relief, the problem was solved. In conclusion, the messages I'd like you to retain are as follows. Innovation requires additional care and skill. Pay great respect to the forces imposed by pre-stressing. Seek to draft contracts that are explicit and clear on risk and who is carrying it. Remember, the method of construction must be the contractor's responsibility, but the designer must check it will not damage the structure. Beware the peer review. Always there will be matters to address and changes may be needed. In consequence, you need to make sure this unexpected work is recognised by your Commission. If you're going to do something innovative, you need to commission it carefully, and if you'd like me to expand on my ideas on how you should do this, I'd be happy to do so in question time. Once there has been a failure, its cause can be so obvious, uninformed people will seek to blame the designer or assume incompetence. What might have been hard to perceive suddenly has become very obvious. And finally, it is never too late to fix a problem. That's my presentation. Happy to try to answer your questions. I think you will all run into this issue in your careers frequently, where you have an idea that will help the client. And I can think of one case, and I won't describe the project, but effectively, the engineer in charge gave a really good solution to a problem the client was facing that was very innovative. But he neglected to explain to the client what a good job he was doing for him. And in the end, innovation, because it hasn't been done before, you need to have a bigger contingency, because you will spend more money, because you run into things not unexpected. Hasn't been done many times before. So he did a wonderful job, had a problem and had to ask for more money. The client got really annoyed, and the consultant had to pay that extra cost himself. So did a wonderful job, ended up with an angry client and out of pocket. Now what he should have done, and what I would recommend you all consider doing whenever you are looking at innovation, first of all, what is the traditional way of solving this problem? And I'd go further and say, what is the gold-plated, Rolls-Royce way of solving this problem? What does it cost? What does the normal solution cost? And it'll come into assessment of operating costs and capital costs, all of which are relevant. And then your innovation, but include a bigger contingency, twice what you would normally allow. And then the client makes the decision. Now, by doing that, the person, the project I'm thinking of, he said, I couldn't explain that to my client. They'd never understand. And that was arrogance. Take your client along with you. Let them make the choice. They're the ones who are going to get the benefit of the innovation. Therefore, they should carry the risk. If you don't go through that process, you are carrying the risk. Is that clear? I think you can do that frequently. And innovation is at the heart of what we do. It's what you should all be seeking. How can we do things better? But when you do that, you need a bigger contingency. Aaron.
You mentioned the collapse of the viaduct in Spaghetti Junction. I'm sort of intrigued on, you mentioned it went through into arbitration and perhaps into court. Did that process end up defining quite well the principles of responsibility in regards to temporary works that sort of survived till now?
Well, it was a fascinating problem, and the arbitration was led by a QC who didn't know anything about construction. I didn't think he was particularly well placed to, but stop and think about the issues. Who should have, there are a number of issues there, a number of parties involved. There was a contract written by the Ministry of Works. They're pretty draconian contracts, those old contracts. But the Ministry used to interpret them, administer them in a fairly friendly way. The contract was drafted by the Ministry, and the designer was a branch of the designer would have known about that load transfer. Should the designer have told the contract that was going to take place? For that, the designer needs to owe a duty of care to the contractor. You might be able to argue that the principal owed a duty of care, but if the designer of the bridge was a consultant, he probably doesn't owe a duty of care. Then the other parties involved are the pre-stressing subcontractor. He knew what was going to happen, or should have done. Did he, they're all men in these days, did he alert? Could he have stopped stressing when they would have heard creaking and groaning when they were stressing those cables? Did he owe a duty of care to the contractor, because he was a subcontractor to the contractor? Probably yes. Then the foundation conditions. The foundations had been prepared by the principal. Should the principal have told the contractor about the variability in the ground conditions? Or is that a claim under the unexpected circumstances caused under the contract? And then there's the designers of the false work. Should they have recognized this problem? I suspect that was probably the contractor's own men. But if it had been an independent body, yes, there would have been a duty of care then to recognize the extent of the problem. And then each of these parties would have insurance. What is the role of the insurers in? So you can see how difficult the argument is. In this situation, the contractor ended up paying for most of it, but got money back on a lot of secondary elements. As I say, the ministry, I think, interpreted the contractor in a fairly friendly way. But it would be different if it happened now.
Gavin, with regard to designers' responsibilities and constructors' responsibilities, and I think you said that the designer should never dictate the method of construction.
Yes, you should always have an idea of how something complex will be constructed. But but the responsibility for that method of working that you have specified, you must write a contract very clearly to saying, if you take this over, that's your responsibility. Because in the end, the person in control of the work has to be the one who's responsible for the work. And as a designer, you're not in charge of the work. And if something goes wrong, you must not put yourself in a position of carrying that responsibility. Yes, you must never design something that's impracticable, that can't be constructed. But the responsibility for the method of working has to be the contractors. Because you don't have the authority, you're not supervising, nor having detailed control over what the contractor is doing. So you don't want to assume part of that responsibility.
Very good. I think we'll leave it there for this evening. And I'd like to thank Gavin for his time and he put on some very interesting points about extra care involved in innovation, importance of pre-stress, and how important peer review is. So I'd like to present Gavin with a first time this evening, and I'm sure you'll all join me in the usual fashion to thank him.